From 2-7, Chanel.
Number 11, I think.
Number 11 with the graph.
Yeah, so I use physics to solve it, but I want to see how you use calculus to solve it.
Sure. It'll probably feel pretty similar.
Yeah.
All right, starts moving to the right along a horizontal line. The graph of the position is shown. When the particle is moving, when is the particle moving to the right? When is it moving to the left? And when is it standing still? Okay? So, moving to the right, your position should be, or the graph of position versus time should be increasing. So I would say, okay, well, those sections are moving to the right. And the position, or when we're moving to the left, our position should be decreasing. So that should be the decreasing part. And when it's holding still is when our position is constant. That's it. So to draw the graph of the velocity function, I'm going to have, this thing's going to have some discontinuities to it. So on this section, going from 0 to 1, the slope is 3 for this. So if I have like 1, 2, 3, so we'll just have like.
So it's open dots because it's like moving like at that point.
Yeah, I would do opens the whole way through. And we'll see why. If you did them closed and one end open, one end closed, that I wouldn't mark that wrong in this context, but we'll see today as to kind of why I'm putting opens instead of. But at this point, I don't know that you would be able to come up with that on your own.
Okay.
On the section from 2 to 3, where do we go? We went down 2 units, so the slope should be -2.
Okay.
So I would have like there, and then we're back constant for 1 unit of time. So like, I guess we extend this out a little bit. So again, not moving anywhere. And the last one we're going, we went over 2 and up 2, so the slope would be 1. That last circle I should have, I guess I could do that. Looks like it's stopping, doesn't it? It's not keeping going. Let's hope.
Yeah, I solved it the exact same way.
Yeah, it's same idea, right? Like, I'm just looking at the slopes.
Yeah.
And then it's constant over that, the slope is constant on a straight line, so just horizontal line for that section, whatever the slope is on that section. But yeah, same idea as probably you did in physics. I wouldn't imagine it being too much different. Cool. Christian. 8? Yeah, sure. So I think this one, depending on how you went about this, could go from like not too bad to real bad. Let's see, equation for the tangent. Okay, so need to start off by getting m. So to do that, let's try doing this one. Check that formula before I write it down wrong or something dumb. Yeah, okay. So I'm going to do that version. I think it'll probably end up being simpler because I will only have really like one complex fraction in there instead of having 2. I suspect that'll make life a little bit easier. I'm not positive, but you could have certainly used the H version, and you should still get the same answer. Let's see, when I plug 1 in, I get 3 on top and 3 on bottom, so that's just going to be a regular old 1. Let's clear the complex fraction. So I'll just multiply the top and bottom by x plus 2. So when I multiply it to there, the x plus 2's cancel, and I'm left with just the numerator. When I multiply it to there, I just multiply the negative 1 through, so I distribute that negative 1. And the bottom I'm just going to leave as is. When I combine my like terms, I get x minus 1 on top. And that's lovely because I see that I can reduce that out, and that part was the problem area. So when I apply my limit, that was probably easier than doing it the H way. Yeah. I think in general, if you get like a rational function like that, that version is probably going to be a little bit neater than the H one.
H one was pretty messy.
Yeah, you did it that way. Yeah, it gets to be a lot, and it's easy to lose track of kind of like where you're at. This was nice because you only ended up with one fraction inside of your fraction, and boy, that makes everything a little bit simpler to kind of hang on to. Does that feel okay? Just so you know, if you did the H way, it still should work. Just might have been more. Others from the homeworks. Giselle. 16? Sure. Okay. The displacement in meters of a particle moving in a straight line is given by S equals yada yada yada, where t is measured in seconds. Find the average velocity over each time interval. As soon as I see an average velocity question, I'm giving this many intervals. I'm doing this stuff all on my calculator. So like I showed you guys before, I'm going to go to the y equals. I'm going to go ahead and type in my function here. And then average velocity is just a slope. So I'm going to do fraction command, and I'll do vars, y vars function y1 of x2 minus vars y vars function y1 of x1 over x2 minus x1. And now I'm just going to go in and update the 3 to be 3.5, and then 5, etc. So I can just go back in and rip these off real quick. Chanel?
Wait, so what equation are you using here?
The slope formula.
Oh, just y2 minus y1?
Yep.
Okay, so wait, so why did you put it in like as an input? Like for
Well, the y coordinate for this function when x is 3 is I'm doing like a function notation on the calculator and having it do the plug-in for me.
Okay.
You know, so I'm just doing this. Giselle, is that okay?
Yeah, I was trying to do it manually, so that's probably the issue.
Yeah, I mean, like, I get it, but like, I don't want to just to be like, I want to do it so I know I did it right. I'm just going to let the calculator handle like all the heavy lifting. It's so easy to make like an arithmetic mistake.
Yeah.
Doing that kind of thing.
So you just put in the like line thing typing into the y equals, and you just press y bars, and then you enter them into the y1.
Yeah, so this is like a function notation, right? So it's like f of 4,
Yeah.
right? My f of x is just in the y1 spot. So it's just treating it like a function notation. So that's the y coordinate when x is 4 is what it's giving me for the function in y1. So like that just makes my life way, way simpler. The instantaneous velocity for this, I would go ahead and I'll do that with the limit. Actually, we'll do 4. So when I plug in 4 plus h into my function, I get 16 plus 8h plus h squared minus 8 times 4, 32 minus 8h plus 18, and then minus, I'm just going to do that in my calculator real quick, bars, y bars function, y1 of 4, 2 over h, oops, what'd I forget? The limit. All right. So I have 16 and 18 is 34 minus 32 minus 2 is 0. Well, that's what I expected to have happen. And if I reduce the h's, I'm left with the limit as h approaches 0 of 8 plus h minus 8. So that is just going to be 0. Is that the right answer? I guess this wasn't an odd for us to check. A little surprised by that result. I mean, it's certainly possible. I just want to double check my answer real quick before we move on and act like everything's honky-dory. Okay, so that should be 0. That's good.
The velocity after 4 seconds is low velocity.
Yeah. So what's that mean?
It's staying still.
Right. Is that, or it's from a, like if it's moving, it's like changing direction from forward to backward. Since it says it's like moving in a straight line, right? Could be standing still, or it could just be in the process of changing from forward to backwards or up to down or whatever. Yeah, down to up, right to left, left to right. Could be one of those spots. So that's certainly possible. And then part C says to draw the graph of S as a function of t with the secant lines with the average velocities or whatever. Okay. So what do we had here? We had 3.5, 4, and 4.5, and then 5, something like that. So I would have like, there's my instantaneous velocity, right? At 3, it said the slope was 1. At 3.5, it's like a half. I can put it that, like that. At 4.5, it's like negative a half. At 5, it was negative 1. So that's kind of what you're seeing. Oh, I should, it said secant lines, not tangents. Those are all tangents. So 3 to 4. So like that. 3.5 to 4. It's like that. So that's what we're doing. 4 to 4.5. It's like that. 5 to 4 is like that. So that's their picture. I'm sorry. It said secant lines, not tangents. But that's the gist of it. Giselle, this was one you asked about, right? Does that feel okay?
Yeah.
So the picture you should notice is that, like, as I get these secant lines are getting closer, you see them flattening out. I expect as they get infinitely close, you're horizontal. Everybody okay? Let's start 2.8. Okay. So in 2.7, what we did is we calculated the derivative of a function at a fixed value a, right? You guys remember doing that? Where f prime of a is equal to limit as h approaches 0 of f of a plus h minus f of a divided by f of h. I'm sorry, divided by h. Here, we're going to change this conceptually, but algebraically it remains identical. Instead of a being a fixed value, we're now going to use the variable x. So now when we take the derivative, instead of getting a number that gives us the slope of the tangent line at the point x equals a, we're getting a function f prime of x that is a function of slopes of tangent lines for any x in f of x. Now, what does this mean for us algebraically? We're doing the exact same thing. We're just replacing the a's with x's. That's it. Okay? Let's look at an example here. So let's start with this picture. So the graph of f is given in the picture below, and we're going to use that to sketch the graph of f prime. Again, because f prime can now be a function, we can represent that with a graph. So this is what I'm doing when I'm looking at this. I'm looking at two things. The first place is I want to look at the maximums and minimums on my function f. So I see three of those guys, right? Each of those maximums, the tangent line, or each of those extrema, the tangent line has slope 0, right? If I drew the tangent line, that's what our tangent line would look like, right? So in the function f prime, those are going to correspond to x-intercepts. So everywhere where your function has an extreme point, a minimum or maximum, those same values of x are going to correspond to an x-intercept, a 0 in the derivative. Chanel.
Oh, why is that? Is it just like a rule or?
Yeah. That's always going to be the case because the slope of the tangent line is always going to be 0 at a maximum or minimum.
Okay.
I shouldn't say always, but if it's a maximum or minimum, it's going to have a slope 0.
Okay.
If the slope, I shouldn't say that. That's too much. It could also not exist.
Is that something further?
Nope, later today.
Oh, no.
All right. So if I look at this section, now I'm going to go section by section, right? What's the slope of the tangent line at every point along that section? It is always negative because the function is decreasing over that interval. So when I draw my derivative, it should be below the x-axis because the slopes are all negative values, right? And that slope is getting closer and closer to 0 as I get closer and closer to that minimum. So it's just going to look like that. Everybody agree? It's the steepest at this end. It's the most negative there. As we get closer to that minimum, it's becoming closer and closer. The slope is getting closer and closer to 0, right? I go to my next section. Here to here. We're positive. The slope is positive on all those points because the function is increasing. Where is it steepest? Probably right there in the middle, right? So that's going to correspond to a maximum on my derivative. So I don't know. I'm going to put it there. Actually, it looks really close to 1. That looks like a slope of 1. I'm going to put it there. And I'll just kind of attach. This section now is all decreasing. The slope on every point along there is negative. The place where it's steepest appears to be like right in here. That looks steeper than -1, maybe -2 or 3 or something. I'll put it down there and just kind of connect them. And then my last section here, the slope along this section is all positive. The steepest place is here, so it just should be kind of going up. Everybody feel okay with that? Chanel?
So I'm just confused. How can you like tell? Like how can you tell, like, for example, like for that, like the steep one, the yellow one in the middle, like how could you tell it was like a minimum and that it was like at that point?
Well, because the slope is negative, right? Okay. And the steepest place is going to be the smallest slope. Be the like -5 as opposed to like the things before it would have been like -4, -3, -2, and the things after would be -4, -3, -2. So it's the steepest place. That has to correspond to the maximum or a minimum.
Yeah, so it's minimum because it's going negative.
Because it's a negative, yes.
Okay, got it.
Yep. Nolan.
So the slope of each x value for f of x is just the y value for the derivative?
Yeah, the slope of the tangent line at any value x equals a for f of x is going to be f prime of a, the y coordinate for the derivative. Exactly. So like if you think about f of x is like x comma y, f prime of x is x comma slope of f of x at x, right? So it's a function of slopes. Giselle, you have a hand.
Can I just go to the bathroom?
Yeah, of course.
Thank you.
Chanel.
So for the first part, the one where the yellow, like the very first part, when the yellow is going down, so how come like, so, okay, yeah, so I think, why is it going up then? Like for the first part.
Well, this is where the slope is the steepest, right?
Yeah.
This is where the slope is the shallowest, right?
Yeah.
Shallow slope is getting closer and closer to 0 because it's decreasing, getting closer and closer to flat. That's why this piece is still all negative, right? All of the y coordinates here are all negative numbers. But as you move closer and closer to that maximum or that minimum in f of x, the slopes are getting closer and closer to 0. So it is the derivative is increasing over that section, but all of the y values are still negative because in f of x it was decreasing for that whole section.
Okay.
Is that?
Yeah.
Okay. It's weird. It takes a minute to kind of like get your mind right about it, but like once you've got it, it's relatively simple ideas. All right, let's do the same thing we've been doing. This time we're going to be using, instead of our derivative being a like f prime of a, like a specific number, Now we're just going to do it in general for an x, and what we're going to end up with is a derivative that's a function in terms of x. Now, what does that mean to us? It means a fat lot of nothing. It means we're just doing the same thing before, but instead of having a's, we're just going to have x's. When I do x plus h cubed, what do I get? X cubed plus 3,
H squared.
yeah, x, well, I do x squared h plus 3x h squared plus h cubed, and then minus x plus h. I'll distribute the negative there. And then when I do this piece, that's going to be minus that, right? Just FYI, Nolan and I, in our head, we were using this multiplication pattern to do that. It's like the perfect cube multiplication pattern. Was probably be helpful in this next homework also. I think there's a couple of cube things in there. Just makes foiling that much simpler if you don't have to do it manually. If you're just like, I can just grind it through the formula here instead of doing it by hand. All right, let's combine some like terms. So x cubed and x cancels out. Everything else has an h in it, so let's reduce some h's. So we have 3x squared minus 3x h to the first plus h squared minus 1. When we do a direct substitution for h equals 0, we're left with 3x squared minus 1. So there's my derivative as a function. Part B says to compare or graph both of them and compare. Well, let's do that then. Okay. So I got what? I have I have x cubed minus x, and then 3x squared minus 1. And that's probably a decent window. So there's, oops. We'll do this real quick. I'm going to go and make the derivative a fat line, so it's a little bit easier to see which one is which. So the skinny line, that's our function. The fat line, that's our derivative. Notice that when the function is at a maximum, the derivative is 0. When our function is at a minimum, the derivative is at 0. When our function is increasing, the derivative is above the x-axis. When our function is decreasing, our derivative is below the x-axis. And then when we're increasing again, the derivative is back above the x-axis. Everybody's cool with that? Chanel?
Wait, so how come, so for the function it's going to like positive, right? Then how come the derivative is going like to negative? Or it's going to negative, like it's going down?
So here, the function is increasing, right?
Yeah.
So that part, the derivative is above the x-axis.
Oh.
Because the slopes are all positive numbers, right?
Okay.
Here, the function is decreasing, so the slopes are all negative, so the derivative is below the x-axis,
Okay.
et cetera, et cetera.
Okay. Thank you.
You're welcome. Okay. Let's look at this one. If f of x is equal to square root x, find the derivative and state its domain. Okay, well, we'll do the same thing, right? And maybe let's do that first. Okay. So when I do x plus h, when I plug that in for f of x, I just get the square root of x plus h. And f of x is just square root of x. So far, so good. If I try direct substitution here, I'm going to get 0 over 0. Wah, wah, wah. What am I going to have to do the limit here? Yeah, very good. Multiply by the conjugate. Again, when you see square roots like that, a square root plus something or square root minus something, conjugates feel like a really obvious choice of what to do. So when I multiply that conjugate through, I get that. Plus. In the numerator, the x's cancel, and then I can reduce out the y. And when I do a direct substitution for h being 0, I get 1 over square root of x plus 0 plus square root of x, or 1 over 2 square roots of x. Does that feel okay? Christian?
The derivative of f, same as like f prime, like the tangent.
Correct. The derivative of f of x is the same as f prime, is the same as the slope of the tangent line for each x in f of x. Yep. It's the instantaneous rate of change. Could also call it that. Yeah, no, these are good vocabulary checks. I like it. All right, what's the domain then of this derivative?
What's it like? Would it be all round numbers except that x equals 0? It's like x equals 0.
Yeah, so you have two things, right? Since there's a fraction, I know the denominator can't be 0. And because there's a radical, I know the numbers under the radical can't be negative. So if I solve this, I divide both sides by 2 and I square both sides. X can't be 0. And if I take here, well, I have x can't be 0, but x is greater than 0 or equal to 0, so it just cancels out the greater than. So we have just x is greater than 0. But what was the domain for f of x?
Yeah, x is greater than.
What do you notice here?
Like 0 is an open dot.
They're different. They're different. So what we're saying then is, what is f prime or f of 0? We know is just the square root of 0. That's 0, right? F prime of 0 is nothing. It does not exist. So what you're seeing here is that the derivative may not exist for every x in f of x. Ooh, this is an idea we're going to circle back to and kind of suss out a little bit more. But think about, this is the way to think about it. If we think about f of x, kind of looks like that, right? If I look at this point, the derivative is a limit, correct?
Yeah.
What's the left-hand limit of this function? Doesn't exist because there's nothing leading into it. That's why the derivative here doesn't exist at 0, because the function is not continuous from the left at 0. And as a result, the limit can't exist there at 0. Hence, when we take the derivative, we need the limit. Oh no! Chanel.
But I didn't understand it. Wait, so why does it not exist from the left?
Because there's nothing coming in, right? The function doesn't come into 0. That's like what the left-hand limit is, what the left side of it's approaching. There's no left side at 0. It's not continuous from the left. It's only continuous from the right. And because the left-hand limits and right-hand limits have to match for a limit to exist, there's no left-hand limit. At 0, what do? It doesn't exist.
So, because like, is it because like you have to have it like continuous in order to see the derivative? Is that why? You gotta have it like continuous, like just like we did in like previous examples? Okay.
All right. I'm going to skip this, actually. This is just like 29 from the homework on the other one, just with x's instead of a's, and it's tedious, and I just don't want to spend 10 minutes grinding through the symbols. What I want to do instead is spend a little bit more time not doing tedious algebra and kind of getting through the stuff that you haven't done. So, notation. How do we represent a derivative? Well, we've seen the f prime of x, right? That's the derivative of f. What if we write the function as like y equals x squared, and I want to take the derivative? Well, you just say the derivative is y prime. Or you could call the derivative dy dx. What's this dy dx kind of look like, though? Oh, sorry. Looks like slope, doesn't it? Dy dx just looks like delta y over delta x. That's slope. That's what the derivative is, right? It's just slope of the tangent lines. Oh, okay. So this dy or this ddx thing is kind of like the operation telling us to do the derivative. So if I have like y equals x squared or something, and I want to do the derivative of this, I do like ddx to both sides. Right? And then on the left, I just have dy dx equals yada, 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 whatever. So that ddx is like the operation. That's the symbol we use to say we're doing the derivative of something. Everybody's okay with that? So the natural question is, like, Mr. Kulik, why do we need like 8 different symbols to do the derivative? Well, we don't need them, but this is kind of what happened. Calculus developed in the 17th century, 18th century, I forget, independently by 2 different people. Isaac Newton in England, Gottfried Leibniz in Germany. Communication in the 18th century. Not real fast. So those ideas and notations these 2 different people used spread. And in some places where you're doing a lot of advanced mathematics with very little contact to the West, like Russia, you keep going and don't contact England for maybe 100 years and share any mathematics because nobody in England can read Russian and nobody in Russia reads English. So like you just end up like with these very specific notations for the kinds of problems they were working on in Russia that are very convenient. And we don't want to give that notation up because in that context, it makes a lot of sense and it's really nice and compact. And in England, we have this other notation we're using to work on these problems over here. And we don't want to give that up because it's really nice and compact. So what do? We inherit all of them because nobody wanted to give it up. Because in specific contexts, each of these notation were really convenient and compact and nice and more intuitive than the other. It's a geography issue. I know, that's not very satisfying, but that's the way it is. All right. Definition. We say a function f is differentiable if f prime of a exists. I'm sorry. We say a function f is differentiable at a if f prime of a exists. So if the derivative of a comes out to be a number, then the derivative exists for that number. Shocking, right? We say a function is differentiable on the open interval from a to b, or the unbounded interval, like a to positive infinity, negative infinity a, or negative infinity, positive infinity, if it is differentiable at every number in the interval. Why is it an open interval, not closed?
Because of the parentheses.
Right. No, I understand. But why is it specifically an open interval? Why didn't we do the closed version? Because if it was closed, you could have something like this. How do I do the limit at the endpoints? There's no left-hand limit or right-hand limit at the endpoints. And I'm into the same problem we had with the square root function earlier. By making it an open interval, I can do the derivative everywhere in there because there's always a left end and a right end because you can't use the end because it's open. Oh, beautiful. Chanel.
Wait, but couldn't you look at the in between for the previous one too, the one with the closed dots?
You can, except at the dot. Like the derivative at A or at B won't exist because there's not a left-hand limit or a right-hand limit at the endpoint. If it's open, I don't get to do the derivative at A. I get to go infinitely close to A, like I get A plus H as small as you want, but not 0.
So that's what, but since you need to like evaluate it at A or something, you have to, that's why it's open.
Yes. So I cannot try to do f prime of A because there might not be anything to the left of A, or f prime of B because there might not be anything to the right of B. Okay, let's look at the function f of x equals the absolute value of x. Where is this going to be differentiable? You know what helps me? Pictures. Let's look at the picture, right? What does the function f of x look like? Or I'm sorry, absolute value of x look like? It's a v, right? Great. If I look at this section, what's the slope at that section? Negative 1, right? Because it's just negative x. Everybody's okay? What's the slope on this section?
1.
Okay. So those all seem differentiable, right? But what about here?
No.
What's the slope at that spot? It's not 0. Doesn't exist. Yeah. Why doesn't it exist?
Close point.
Well, if I look at the limit as h approaches 0 from the left of f of x plus h minus f of x over h, it's negative 1. If I look at the limit as h approaches 0 from the right of f of x plus h minus f of x over h, it's positive 1. So what does that tell you about the limit as h approaches 0? Does not exist. So where is this function differentiable? Negative infinity to 0, and then 0 to positive infinity. Not differentiable at 0. Okay, so this is weird, right? Because this absolute value function is continuous the whole way across from both the left and the right. We don't have the same problem we had with the square root function where we had, okay, well, that derivative didn't work at the start because we didn't have continuity from the left. Here we do. But because we have this sharp corner where the slope changes from negative 1 abruptly to positive 1, rather than a curve, like a smooth curve, where it's getting, it starts out positive, but it's getting closer and closer and closer to 0, and then it tips over and goes negative, that's fine, right? If it has a smooth bump. But if it's a sharp corner where the slope abruptly changes from one number to another, we're going to lose our differentiability there also. So that's a second situation, right? We know continuity is a problem for differentiability. And now we know that like a corner is a problem. And we're going to see one more in a moment. Here, though, the most important theorem in this section, if f is differentiable at A, then f is continuous at A. Differentiability implies continuity. The converse is not true. If a function is continuous somewhere, it does not make it differentiable there. Our canonical example is absolute value of x. Continuous at 0, not differentiable at 0. No one.
But if it's not continuous, then it's not differentiable either, right?
Correct. If you don't have continuity, you can't have differentiability. That's the inverse, or the contrapositive, excuse me. Trying to remember the geometry terms.
Does differential just mean it has a derivative at that point?
Correct.
Okay.
So if I do f prime of A, that's a number. That's all it means. Chanel.
So how come for the absolute value example, you evaluated the limit to see if it's differentiable? I thought it's just like you kind of like, I don't know it. Like,
Yeah, this is, I used the wrong notation here. Sorry. That's why we're confused, right? Yeah. This, that was yucky. Let me do this better. We should have used this one.
so you're just evaluating the limit at that point to see if it's differentiable. And if they don't match up, then it's not. That's
Yeah.
it?
Yeah, because this derivative is just the slope of the tangent line, right?
Yes.
Well, the slope everywhere here is 1. And the slope everywhere over here is -1,
Oh, okay.
right? So I don't really need to grind any numbers. I'm not going to push symbols. I have the picture, and I'm just using the picture to do the limit. You know what I mean?
Yeah.
But yeah, because those things don't agree, it tells me at 0, our derivative isn't going to exist. Okay. The number one place where this theorem comes into play is on the AP exam. They'll say, blah, 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 where f is a differentiable function, yada, yada, yada. What that also tells you then is that f is continuous, where you might need that to do an intermediate value theorem or something else, like a mean value theorem that we haven't talked about, or a something else theorem from in the future, where we might need continuity. We'll get it from just differentiable. And that's a really common phrasing on the AP exam, particularly on a free response question that's including could possibly be parts A, B, and C coming from different chapters of our textbook. Okay. So here's the big putting this together. So we've seen that derivatives fail to exist when we have a corner, like the absolute value of x. We've seen that fails to exist if we have discontinuity or don't have full continuity, like the square root of x. The other place where derivative can fail to exist is if we have a vertical tangent. So if we look at this last picture, does anybody know of well, there's a common function that you all know that would have a vertical tangent in it. You'd have talked about it in Algebra 2. Anybody recall? It's not a log. I mean, it cannot without really just telling you. It's not x squared. It's the cube root of x. What does the graph of that look like?
Yeah, it's kind of like that.
Looks like that. What do I have right here? That vertical tangent.
Oh, it cuts through it. Like,
Because if I try to draw a tangent line here, it's a vertical.
oh.
So those are like your three canonical examples. Extremely common multiple choice question. I give you a graph and ask you, where does the derivative fail to exist? What do we look for? Corners, discontinuity, vertical tangent. That's it. Super common AP multiple choice kind of question, where we give you the picture and ask you where the derivative fails to exist. Or ask you the intervals in which it's differentiable, where, again, you're just doing everything except for the places where those are at. Shana.
Why is a vertical tangent cause the derivative to not exist?
What's the slope?
Like,
Infinity one direction, but negative infinity the other.
oh, so both does not exist.
So the limit doesn't exist because it doesn't agree.
Okay.
Yep. Right, because if I look at the slope here, it's going negative infinity. This slope there is going positive infinity. Vertical tangent doesn't exist. Okay. So we've seen we can take the derivative of a function. What do you get if you take the derivative of a derivative? You get another function. It's called the second derivative. So if I take the derivative of dy dx, you get d squared y dx squared.
Wow.
Let's do one. You're like, oh, this looks terrible, Mr. Kulik. It's not, though.
Scary.
So this was a problem we did already earlier in the lesson, right? We have already the derivative is 3x squared minus 1. We did that problem earlier. So if I want the second derivative, same idea, right? Just I'm plugging into the derivative instead of f. So when I plug x plus h into 3x squared minus 1, I get 3x squared plus 6xh plus 3h squared minus 1. And then if I write minus f prime of x, I get minus x squared, or 3x squared plus 1. Oh no, what'd I forget? The limit. It's the beauty of doing this in OneNote, right? Okay. I noticed that negative 3x squared and positive 3x squared, 1 and 1 all cancel out. I said 6xh. I don't think I wrote the h. And then I can reduce my h's. And so my limit here is of 6x plus 3h, or just 6x. All right. So far, so good. So, physics, position, velocity, acceleration, all related, as they are all derivatives of each other. So if I take position and I do the derivative, I get velocity, aka the first derivative of position. If I take velocity and I do the derivative of it, I get acceleration. That's the derivative of velocity or the second derivative of position. There's actually a third derivative of position. Does anybody, physics students, remember what this is? It's called jerk. It's named after you. Ha 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 ha. This is the first derivative of acceleration. It's the second derivative of velocity or the third derivative of position. These things are all nicely linked together. The AP loves to do these physics problems where you have to like do a bunch of derivatives on something and use like the values of acceleration to find the things in velocity and to find the things in position, where you have to go back and forth between the different equations. But they're all related. If you have the position or the equation that describe position in general in physics, you can then differentiate to get the equation for velocity, differentiate again to get the equation for acceleration, et cetera, et cetera. I know.
Problem. You have to find like the J value.
Here's the lovely part though. These derivatives seem so hard to do right now. In like one more section, we're gonna take what was like a 10-minute problem and turn it into like a 10-second problem. So like, yeah, like the next 4 or 5 sections of chapter 3 are just shortcuts for derivatives. It's like, how do I do a problem like this without having to do the limit? And just use a formula. That's like the next 4 sections. So we're almost there, guys. It's gonna be beautiful. You're gonna love it. You're gonna be like, wait, what did you just do? All right, so we have third derivatives. Let's do the third derivative of that problem and the fourth derivative of this problem we just looked at. So recall, we already found that f prime of x was 3x squared minus 1, and that the second derivative was 6x. So let's find the third derivative. So when I plug x plus h into f double prime, I just get 6x plus 6h. Don't forget your limit. And minus f prime of, or double prime is just 6x. The 6x's cancel, the h's reduce, and my limit is just 6. Oh, all right. If I do the fourth derivative then, the triple, f triple prime minus, or f triple prime of x plus h minus x triple prime of x. What is f triple prime of x plus h?
6.
Yeah. And what's f triple prime of x? 6. So what am I getting? And any derivative after this is going to be the fifth derivative, sixth derivative, seventh derivative are all going to be just zeros.
Wait, how is it 0? Because what if you plug in 0? Isn't it?
No, if I plug 0 in, I just get 0, right? Right? This is just a constant function like y equals 0. When x is 7, what's y? 0. When x is 15, what's y? When x is negative 13, what's y? When x is just a, what is y? 0. So just always 0. You know what I mean?
Is that every case?
No! This is particular to polynomials. Some functions you can differentiate all day long and they never go away. Or never become, the derivative never becomes constant. But a polynomial will, eventually.
Or-
No,
No.
eventually.
Okay.
we'll see real quick as to like what the limiting factor is to know how long it's going to take before it becomes constant. It's not hard, but we're not there yet. Chanel.
Wait, so, but is this 6 minus 6 over h?
So 0 over h is 0.
0?
So the limit of 0 is 0.
Oh,
So I'm doing that. I'm not plugging 0 in for h.
oh, okay.
I'm doing 0 over h is just 0. And then I do the limit.
Oh, and then you do, okay.
Here, let's write it in.
Okay.
That's
I
a
was like,
that
what
no,
did you
that's
do?
that's a good point. It's a really good point. It was unclear. That's better. I just got excited because I noticed I didn't have the homework highlighted for yours, so I was going into second hours to steal that piece so that the highlights weren't there. Oops. So let's do Sunday.
2.1,
2.1 and 2.7. 2.8 that's assigned today, not due till next Sunday. Everybody's cool? Okay. How are things going with the math? Are these sections, is it starting to feel like it's less theoretical, a little bit easier? It gets way easier in the next 4 or 5 sections, I think. I shouldn't say easier. Becomes more familiar. Becomes very computational.
We're just like plugging something out of it.
Just like using the formula to do it. Using the formula to do it. Even these problems where we're doing the derivative, it's like the same kind of limit every time. It's like usually not, I mean, some of them can be tedious, but it's not difficult to figure out what to do algebraically. It's just sometimes hard to keep track of all your symbols. And I make it look really easy when I do it because, again, thousands of hours of practice makes it look effortless. When I was doing it the first time, I made all the exact same mistakes that you're making the first time you're doing it. It is perfectly normal to, like, every time I do one of these things, I do something dumb and mess this up and can't get the right answer, even though I feel like I'm doing the right thing because I foiled something wrong, or I forgot to write something down, or I didn't plug x plus h into all the different parts of the x's. I just forgot like the -1 at the end or something, like I've done it all a bunch of times to the point where I don't do it anymore, but that's normal. It just, a lot of times we have to slow down and be careful and maybe write down more than Mr. Kulik writes down when he's doing his problems. That's okay. If you need to take a page to do it, take a page to do it. Write out all the little nitty-gritty details if you need to, until you get comfortable with like what you're doing every time, and then you can start being a little briefer once you're confident that you aren't going to forget to do stuff. But we're, I would say 3.1 through 3.4 or 3.5 even. Yeah, really, I think all of chapter 3 is pretty easy with the exception of 3.9, which isn't even on the next part of either of the next 2 tests. I think it's some of the easiest stuff we potentially do, but you just have to be careful. Just have to be careful. So we'll look at, start building out really most of what chapter 3 is like, okay, you know what a derivative is now. Here are the shortcuts. Here's how we're actually going to do derivatives in practice, because no one, once you get a complicated function, wants to deal with trying to do a limit and using like trig identities and like all kinds of mess to try to get things to cancel out to where you can do your direct substitution. Like, that's a nightmare. We just want the shortcuts, which is all about what we're building through 3/6 or so is just building out shortcuts. To do like this problem, f of x equals x cubed minus x, something you can do in your head in 3 seconds. In one section, we'll be ready to do that. And in fact, as ugly as I can make the polynomial, you can do it in 3 seconds. And we're one section away from that shortcut. Yes. Which will dramatically simplify the amount of work you need to write down for your problems. Logan? Nope.
Why isn't the power rule come before?
Because it's a shortcut.
Can't remember the shortcut.
You always do the general version before you do the shortcut, because you need the general version to prove the shortcut.
I don't care about the shortcut.
The good news is you'll almost never be asked to use the definition.
Are you gonna be asked to use it on the test?
What you'll certainly see on the AP exam is you'll have like, there'll be like what is, and then they'll say limit as like h approaches 0 of like 8 plus h to the 10th minus, let's make that 2. Like this. Here's what you recognize. You go, okay, this is just the function that I'm differentiating is x to the 10th at x equals 2. And then you do the derivative shortcut and plug in 2. You don't do the limit. Like you just need to recognize this form going, okay, that's just the derivative of x to the 10th. And I'll do it the shortcut way. So like that's how they're going to get you with the definition of the derivative, is they're going to like give you a problem like this where you need to take it apart to get the thing that you just want to do. You know what I mean? Very rarely do they ask you to like use the definition of the limit to do something. Maybe like one part of a free response question, maybe, but that would be the extent of what you're going to see. So by and large, it's just like use the shortcuts, use the shortcuts, use the shortcuts, use the shortcuts. And they're going to do the definitional stuff with graphs or table where you don't really have to do like the crappy limit. You just have to be able to think about it in the appropriate way to like figure out what's going on from the graph or the table or whatever. Which again is fine because it's not a page of writing, But that's my experience anyways from the things that I've done and the things I've looked at.